tangent line approximations. The key idea is if you have a curve, yeah, go. I'm going to record all this. You can watch this. Make sure you have the right 5. There were 5 approximations that you had to do on this worksheet. All 5 of them have to be correct. Okay, so you have a curve, and you have a tangent line to the curve, right, touching at a point. And the key in this whole idea of differentials and deltas, or tangent line approximations, is that if you are near this point of tangency, the function, the curvy function, can be approximated by a line. And lines are easy to do. Lines are like Algebra 1 stuff, okay? And the curves can be pretty complicated. It could be a square root or a cube root or a sine wave or a log function or something really complicated. But if we want to figure out, you know, functional values, you could use a tangent line. And if you're close to that dot, the answer is going to be really close. That's the idea. Okay, so if you looked on this page in the book, page 190, you saw that the function is close to the line, and the line is given by this, f of c plus f prime of c, x minus c. And you should probably have that formula sort of memorized, if not today, then certainly tonight. Be ready to use it tomorrow. Where does that come from? Well, it comes from this point having coordinates c and f of c, right? Y is f of x, right? And the slope of this green line, this m tangent, the slope of the tangent line is given by the derivative evaluated at c. So that's where this black equation comes from. It really is Algebra 1, believe it or not. Let's look at a couple of examples. This is one that I found on a released AP test. The function f is twice differentiable. It's sort of hard to see what this says. Let me rewrite it up here. F of 2 is supposed to be 1. F prime of 2 is supposed to be 4. And F double prime of 2 is supposed to be 3. The directions say, what is the value of this approximation using a line tangent to the graph? So the idea is you have to write down the tangent line and then use it, chuck in 1.9, and you get one of those answers. And you go, Chase, I'm supposed to be able to do that? Yeah, and this is probably about a 30-second problem, maybe less than a minute. I mean, for these multiple guess problems, you got to average about 2 minutes a problem. It's like the quickies. Some of them are going to be easier than others. This one is a quickie. So let's see. The line is supposed to be a y value, f of c. And then it's supposed to have a slope times x minus c. So if we use the information that we have here, L of x is equal to 1. That's the y value. Slope, 4. X minus 2. That's the c value right there, right? So notice that this right here, this is saying f of c is equal to 1. F of 2. So this is 2. There. So that's the line, and that's about the same as the function. Okay, so just go ahead and put 1.9 there, and there, and there. Pick an answer, and you're done. There was no calculator on this. Hopefully you can do simple arithmetic. Just put 1.9 right there after the f. F of 1.9. It's about the same as L of 1.9, which is equal to 1 plus 4 times 1.9, take away 2. So what's that? Negative a tenth? Okay. Times 4 is negative 4/10. 1 minus 4/10. Answer. Okay. Okay? Okay? Okay. Here's another one. I dug through some old tests and just found some questions. F is a differentiable function. It tells you f of 3 is 2. It tells you f prime of 3 is 5. If the tangent line to the graph of f at 3 is used to find an approximation for a 0, then that approximation is one of these guys. So again, the function's about the same as the line. Go ahead and write down the equation of the line. It gave you all the pieces. You just write it down. And then you're going to have to think a little bit, what does a 0 of a function mean? That was sort of the algebra 2 pre-calculus idea. 0 of a function. Anybody know what that means? Y is equal to 0. Give me another interpretation. On the graph, x-intercepts, right? Okay, so all these mean the same thing, right? So 0 functions where the function equals 0 or where it crosses the x-axis. Okay, go ahead and tell me what the 0 is. It's got to be one of those three numbers. Okay, equation of the line. What do I start with? 2. All right, that's the y-coordinate. Plus 5, that's the slope, x minus 3. There you are, good. So our function is about that. This function, we don't even know what the function is, but it's almost this side. It's 2 plus 5 times x minus 3. See if you can find the 0. Remember, 0 is what makes this thing 0. So this is 0, right? What makes it 0? Answer? 2.6. Yeah? I hope. Okay. So, I mean, obviously, you're just solving this equation. What this is 2 plus 5x take away 15. So chuck that over there. That's 13 is equal to 5x. So x is 13 fifths. And 2.6. Okay, one more, and then we'll get into your worksheet. This was sort of a convoluted problem. It says the function f is defined between 0 and 8. The graph of its derivative is right here. This is the graph of the derivative, f prime. It tells you the point 3,5 is on the graph. The ordered pair 3,5 is on the graph of f. It should be pretty clear that this is not f, that's 3,2, right? 3,5 is on the graph of f. We don't have a picture of f. We do have a picture of f prime. And the task is find the equation of the tangent line. And it's got to be one of those 5 choices. I did tell you in May you're going to get 4 choices. I sort of changed up the test a little bit. So I suspect in some ways this is a little bit harder because there's one more distractor. See if you can find the equation of the tangent line. And then which one is it? Okay. So L of x is equal to the y-coordinate, 5, right? There it is, plus 2. Where'd the 2 come from? I don't see 2 here. Where does 2 come from? There it is. This is the derivative, right? So we need the derivative at 3, and that is this point up here, which is 2. Okay, so the derivative at 3 is 2 times x minus 3. Okay, so it's got to be one of those guys. Which one is it? A, B, C, D, E, C? Yep. So you see the 2 times x minus 3, and then this 5 would go over there, right? Okay, tangent line approximations, lots of applications. I gave you a couple here. This first one had to do with the square root curve and the point 110. I mean, you should realize square root curve looks like that. If this is 100, then y is the square root of x is 10. And the task was to try to use this tangent line right here, right, that touches the curve at that point to approximate the curve. And I sort of worked you through it here. Here's our tangent line equation again. Make sure you have that down. If you put c is equal to 100 in here, the first thing you'll note is that the slope of the tangent line is 1/20th. 1/20th. I worked that out here, right? F prime of c is 1/2 square roots of c, which is 1/20th. That's the slope of that. So the equation of that line is right here. And my Chromebook. I actually had someone ask me, is this the real thing? It's cracked. I'll have to glue it back together again. But that's the nice thing about crazy glue. What's anybody else? We'll live. Not to worry. I figure if Napoleon's men can put a big scratch, I can crack it. That's okay. Okay, well, let's hope that guy works. Otherwise, they're all going to be upset. Okay, where are we? That's the y-coordinate right there, right? Y-coordinate is 10. The slope is 1/20th, x minus 100. So you can use that to go ahead and approximate, right? This is the square root of x is approximately equal to 10 plus 1/20th times x minus 100. So if I want the square root of any number close to 100, the key is it's got to be x is near 100, then you just put it in there. 100.37 is about 10. In my morning class, I have some people that are math challenged. Okay. If I said, what's the square root of 100? They will tell me 10. That's great. And if I say, what's the square root of 121, after taking off a shoe or two, they can get to 11. They got that. Right? But if I said, what's the square root of 102, they'd be clueless. They have no, it's not a number. And I'm going, of course it's a number. Could you at least guess? Well, it's maybe 10? Well, yeah, it's not exactly 10 because square root of 100 is 10. Now, our problem is maybe a little bit more sophisticated. I want the square root of 100 point, what was it? 37? 37 like that? Would you agree that it's almost 10? Is it more than 10 or less than 10? More than 10, right? It's between 10 and 11. Well, that's what this says. This says that the square root of 100.37 is about 10. Plus this much. 1/20th, now you just have to put in 100.37. And I did that right here. Okay, so that's what, 37 hundredths, or that's 37 over 100. So there you are. This is my approximation. This is what my calculator gave me as the best that the calculator can do. It's actually wrong because this is supposed to be irrational. It goes on forever. But that's pretty accurate to 9 or 10 decimal places. Is my approximation too big or too small? There's my approximation. Is that too big or too small? Why would it be too big? No, I didn't round. I didn't round at all. I just worked this calculation right here. That's what I did. Why is that approximation too big? Yeah. Duh. But why isn't it too small? Here's the curve. Here's the tangent line. Why is the tangent line approximation too big? The curve is going this way, isn't it? Yes. Okay, so if this were my, again, not to scale, this is 100.37. The exact value I want is this one right here. That's the one that's on the curve. right? That's the one, that's the value I want. The one I'm getting is the one up here on the tangent line. I'm getting this number. Does it make sense that the tangent line approximation is a little bit too big, right? Because the tangent line is above the curve. Yeah, okay. And it is a little bit too big. Let's try another one. Okay, so again, 98.5 is close to 100, so I'm using the exact same tangent line to approximate this, and I did it. Here's the square root of 98.5 is about 10. Yeah, duh. But now notice that when I put 98.5 in here, this is negative, so I'm taking away a little bit. It's a little bit less than 10, and 10 take away 340, this gives me that. This is what the calculator gives me. Is my tangent line approximation too big or too small? Too big. Again, isn't the tangent line above the curve? There's the curve, there's the line, right? It didn't matter whether I was to the right, I was too big. If I was to the left, I was too big. When would I be exact? Which x value? Not 10, 100. You put 100 right there and you put 100 right there, don't you get the right answer? Yeah. This is good for numbers near 100. It's exact if x is equal to 100. Okay. Okay. Square root of 50. Using 100 doesn't make any sense. Okay? And here's the idea. Here's my curve. I know I have this point over here. This is 100, 10. And I also have a point 50, 7. 50, 7. Sorry, 49, 7. Square root of 49 is 7. Yeah? Okay. And what I want to do is I want to draw a tangent line that's going to be close to the graph. I'm looking for, if this is 49, I'm looking for the square root of 50. I'm looking for this dot right there. How high is that dot on the curve? And the tangent line that I had over here was like really good for numbers near 100. But if you look over here, it's not really good for numbers near 49. So to get a more accurate approximation, I should probably draw a tangent line close to 50, and that would be this one here, right? So I should be able to find this blue dot pretty easily. That's on a line, and I'm going to use that to approximate the green dot, which is on the curve, which is what I really want. Okay. So I've given you the slope. Hopefully you did verify that the slope does work out to be 1/14. Everybody? Okay. So the square root of x is approximately 7 plus 1/14 times x minus 49. Right. What kind of numbers is this good for? Numbers near 49. If you put 49 in there, it's exactly, it says 49 is approximately 7 plus 1/14 times 0. Not an approximation if x is 49, but if x is 50, this is good. Okay, so square root of 50 is about 7 plus 1/14. Okay, that's what the calculator says. If you want to see what 7 plus 1/14 is, I don't know my fractions very well. You get that. And again, a little bit too big. Okay? Close, but a little bit too big. Square root of 20. You've got a couple ways you can do it. One of the problems with the square root of 20 is that there's not a nice point real close to it. Here's 20. We have a point over here that we know, which is 25.5. And we have a point over here that we know, which is 16.4. And we're trying to figure out the point on the curve at 20. That's the number we want. And so if we do it two different ways, if we draw this tangent line like that, we'll get a point there, which will be a little bit too big. If we draw the tangent line over here, right, we'll get a point here, which is still a little bit too big. So you should do this two ways. Okay, so let's go ahead and knock this guy out using the blue tangent line for starters. Okay, square root of x is about, if we're using this point, the y coordinate is 5. The slope is 1/10. You should verify that, x minus 25. If we were using the black line, and then the square root of x is about 4, and the slope there was 1/8, and then x minus 16. Both of these are reasonable approximations to use for numbers between 16 and 25. If I was real close to 25, I'd rather use this. If I was real close to 16, I'd rather use this. Okay, 20 is sort of in between. So, I mean, if we use this guy, the square root of 20 works out to be about 4 plus, what's that, 20 to 4/8 plus 1/2, right? So that's my approximation there. If I'm over here, the square root of 20 is about 5 plus, put 20 in there. So what's that, negative 5/10, right? So 4.5 again. Now, both of those are rather crude. Here's the better approximation, 4.47. You know, I guess 4.5 is not that terribly bad, but it's not super accurate. In fact, if I, pick on my discrete math class again, if I said the square root of 16 is 4 and the square root of 25 is 5, and I said, what's the square root of 20? Almost everybody would say 4.5, right? Which is the tangent line approximation. Now, they don't know that. They would just pick a number between 4 and 5. And it just so happens the tangent line gets to that location. Okay. Cube root of 9. No longer square roots. Cube roots, different function, different derivative. Here's the derivative. Okay? I told you that the derivative at 8 is 1/12. You should verify that. Here's the equation that we're dealing with. The cube root of x is approximately 2 plus 1/12 times x minus 8. This is good for numbers near 8. Good for x values near 8. Right? Anybody unsure where the equation came from? Okay. So, square root of, or cube root of 9 is about 2, which I think most of you would agree. The cube root of 8 is 2, so the cube root of 9 is about 2. And then add 1/12 there, because you're putting 9 there. Okay, so once again, just sort of comparing with 2 plus 1/12 is that guy. And here's what my calculator gives me. Okay, so you see I'm not terribly bad. Too big or too small? Let's see, here's my approximation, 2 plus 1/12, 2.0833. That's what my calculator says, 2.0800. My approximation's too big. Here's the graph. Right. Here's the point on the graph, 8,2. And sure enough, the tangent line is above the graph. The tangent line approximation would be too big. Okay. If we were over here, would the tangent line approximation be too big or too small? Too small. The tangent line is below the graph. Yeah. This approximation is only valid for numbers near 8. That's what you need to know. It's close for numbers near 8. That's what you need to know. You don't want to get away from 8. And you're stupid, because it's not for numbers away from 8. You just don't do it. Right? What happens if I press on my accelerator hard on the interstate? I go faster. That's what works. What happens if on the interstate I press hard on my brake? That's stupid. You don't do that. People will run into you, right? It's the wrong thing to do. Don't use numbers away from 8. You probably would. And when you're rear-ended by that semi and you're doing 80 miles an hour down the highway, you're going pretty fast too. But that's not because you hit the accelerator. It just so happened to be that way. I mean, I know it's really dumb to cancel the 6s. But it's the right answer. I'll just cancel 6s. I always get the right answer. No. Excuse me. Just don't do it. Okay. We're supposed to raise this to the 4th power. Anybody got an answer for this one? I hope. Okay. So this is now x to the 4th. The function that we're dealing with, x to the 4th, and it's about the same as a line. I gave you the y coordinate, which is 16. I gave you the slope, which is 32, and this will be x minus 2. Okay, so this will be a good approximation for numbers near 2. Now, if we do a real quick sketch, I mean, you should be aware a quartic looks like this. Okay, and here's a point. This is not quite the scale. 16, right, is 2 to the 4th power 16. And I'm drawing the tangent line, which looks like this. Okay, and instead of using 2, I want to go real close to 2, which is like 2 point and a smidgen. And what I want is the point on the blue curve. I'm not going to get the point on the blue curve. I'm going to get the point on the black line, right? And it's pretty clear that it's going to be a little bit too small, but it should be close. This approximation is valid for numbers close to 2. So let's go ahead and chuck it in and see what we get. 2.013 to the 4th is about 16. Like, duh. I mean, doesn't that make sense logically right off the bat? It's about 16. Because I know 2 to the 4th is 16. Okay, but now we have to add something. We got to add this much. 32 times, what am I putting in here? I'm putting in 2.013. 0.13, take away 2, right? Okay, so that's my tangent line approximation. If I pull up my calculator and just see what that is, 16 plus 32 times, what this is going to be, 13 thousandths, right? Times 13 thousandths. Okay, so that's my approximation. And if I just say, well, you know, why are you doing this, Bosque? Because you can just punch 2.013 and raise it to the 4th power. I get that. Am I close? Too big or too small? A little bit too small, right? A little bit too small. This is 416. It's supposed to be 420. Okay, so that's a typical tangent line application. One of the more common approximations that's seen in engineering is this. The sine of x is about x. That's a good one to put up your sleeve somewhere. The sine of an angle is about the angle. Huh? Yeah, it's used all the time. Now let's see, if I want the sine of, I don't know, let me pick an angle like 0.025 there. And I get that. Is that about close? Yeah, it's pretty close. By the way, is my approximation, this is my approximation. It's only in radians, right? No, it's in radians. All trig stuff is in radians. No, you're working in radians all the time. Degrees is a high school thing. Trust me. Yes. Is my approximation too big or too small? I said that the sine of whatever that was, 0.0125 is about 0.0125. That's what this says. The sine of an angle is about the same as the angle. That's what my calculator says it is. Is my approximation too big or too small? It's a little bit too big, right? The more accurate value is this guy right here, 0.12499. Say, okay, well, let's try that again. What's the sine of 0.16? Okay, the sine of 0.16 is 0.159. Pretty close? Yeah. Too big or too small? Okay, well, let's just sort of work up here. What is the sine of 0.5? Well, 0.479. So I guess it's reasonably close, but it's getting more and more inaccurate. How about the sine of 0.9? Okay, now the accuracy is really falling off, right? The sine of, I don't know, 5. Well, we know that has to be wrong, right? Sine values are always between plus and minus 1. It can't be 5. So I guess it begs the question, for what x values is this good for? Say again? Well, we could try that, but I think you'd be disappointed if I throw in the sine of negative 30. That's nowhere near negative 30, but negative 30 is less than 1. So try guessing again. For what values is this good for? Say again? Between 1 and 0. So if I pick a value like a negative number, the sine of negative 0.00123669, negative 0.0123668, that's a negative number. What values is this good for? Okay. We missed an important point here. Let's go back. Ding, 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 ding. It has to be close to the tangent, right? Where the tangent is. This is good. This is good because 50 is close to 49. You have to be at the tangent point. Okay, so let's look at the picture. Here's the sine wave. I need a point on this curve. Now there's a zillion points. I'm going to choose the origin. I'm going to choose 0, 0. And I'm going to try to draw this tangent line. Here's the equation of the tangent line. I need the y-coordinate. The y-coordinate, 0. I need the slope. Where does the slope come from? This is a calculus class. It comes from a derivative. We've got f of x is the sine of x. F prime of x is the sine of x. I can't put cosine of x there. I have to put 1. Where does that come from? Cosine of 0. So I have to evaluate this at 0, cosine of 0, which is, okay, there's my slope, and then I do x minus 0. So sure enough, my tangent line is in fact x. So it makes sense that the sine of x is about the same as x. I'm sure you saw this in your trig class. You probably blew it off at the time. Here's the sine wave, and here's the line y equals x. Do they look like they're about the same? Where? Near the origin, right? I mean, if you zoom in, these become less and less different. I mean, you see the wave bending, and the line is going like that. And so it does make sense that the sine value is about the same as the x value if you're close to 0. And if we, that's a number close to 0. Here we are on the sine wave. It's 0.195. Here we are on the line, 0.196. Okay, the line is a little bit bigger than the wave, so this approximation is a little bit too big. Too big if x is bigger than 0, too small if x is less than 0. Okay. The other thing you were supposed to do yesterday was to do some of these antiderivatives and we only have time to do a couple of them. These are on page 196. I would like you to do as many of these tonight as you can. An hour. Read the odds. The answers are in the back. Do the evens. We'll go over the evens tomorrow. 27, or sorry, 27. It said dy was 20x cubed dx, and your task was to come up with y, right? And you should have gotten what, 5x to the fourth plus some constant. Okay. My suspicion is a number of you did it different ways. This is the right answer. Okay, 29. There was dy is sine of 4x dx. And you had to use that differential to come up with the original function y. Again, the angle is 4x, so we're going to leave that alone. But that doesn't quite cut it. Let's see, 1/4 is a help. We're still not quite right. We need a negative, right? Because the derivative of a cosine would be a negative sign. That negative takes care of that. The 4 comes from the chain rule. And then don't forget to add your constant at the end. Okay, so you got a couple of those going on. Probably one of the easier ones was a one like 35. Answer? 5x plus a constant. 33, that's an easy one. Tangent of x, right? Plus your constant. When you get down to problems like 39, or 40, it said be clever or be very clever. Anybody get an answer to 39? I don't know if you got that far or not. It has the sine to the fifth of x. dy is the sine to the fifth of x. It also has a cosine of x and a dx. If you think of it this way, sine of x to the fifth, cosine of x dx, that may sort of help a little bit. The task is, what is y? I need a function that when I differentiate it, here's the derivative now, I get that. 1/6 sine to the sixth plus your constant. Good. The thing that bothers students is like, well, what'd you do with the cosine? Where'd the cosine come from? Why isn't it up there? This cosine is required because of the chain rule, right? The derivative of this would be the 6 comes down, so they cancel. So you get sine of x to the fifth, and then the derivative of sine is cosine. Yeah, that's a toughie. The be very clever one is interesting. We'll do that one tomorrow. Please read 5-3 tonight. We'll do formal antiderivatives tomorrow. I'll get your test back to you as soon as I can. I really don't want them. Amen.
God, by the light of the Holy Spirit, did instruct the hearts of the faithful. Granted by the same Holy Spirit, we may be truly wise and ever enjoy His consolation. Through Christ our Lord.
Amen.
Father, Son, Holy Spirit.
Okay. Mañana. Need a book report in 3 days. Yes, ma'am.
Question.
Yes.
How we get the formula?
Which formula?
LX.
L of x?
Yeah.
Hey, Mr. Can you take me a book report in 3 days?
No, I just want you to read it. First of all, you can memorize it right here. So you should know that, yes?
Yeah.
Okay, so here's how it comes. Okay, here's a point, here's a slope. Remember this in Algebra 1. Right? So for this problem, it would be y minus 8 is 5 times x minus 3. Yes? Let me move the 8 over here. Same thing? Okay, so here's the line. This is a line. This is this number here. This is F of C. This is C right here. No, which are you looking at? For a tangent line?
Um, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
11.
Oh.
Yes.
Well, I guess we will use it
Yeah,
tomorrow.
yeah. That's the one we're using. Okay.
Yeah.
Yeah. They're all the same, but this is the one we were doing today. Yeah, we'll talk about the differentials dx and dy tomorrow. Can you give me a resume about all your marvelous band activities and all your extracurriculars, and what do you do other than sit in my class? That's the only thing you do. What do you want to be when you grow up? A math guy. Yeah, just a resume thing, so I can sort of beef up your. He sat in my class for 1 year. Actually, he sat in my class for 4 months. This is what I know. I know he plays band, or he plays in the band, and he sails, and he likes to chew gum. But I mean, those are the only things I know. Yeah.
I'll send it to you.
That would be fine. When do you want this done by?
Certainly before the 15th.
Okay, so that's a couple weeks away. Why don't you give me a hard copy? That way I don't have to print it out. Hard copy of your resume. Print it out, bring it to school tomorrow. Oh. Bye.